Okay, so it's, I'm very happy today to welcome Christophe Micheyl here as our speaker. Dr. Micheyl got his degrees in France at Lyon University, and he spent some time at Cambridge University working with Brian Moore and Bob Carlyon, leading auditory perceptual scientists. And after a brief stay at CNRS and at Georgetown University with Joe Raschiger, he's been at MIT working with Andy Oxenden for a number of years. He's currently a research scientist there. And his title is Use of a Perturbation-Correlation Method to Measure the Relative.
Right, so I should start this talk by saying that, is the mic on, by the way? Yes? Sorry. And by saying that this is not my main line of research, it's some sort of a side interest for me, and this is work that we've been doing with my friend and colleague, who was then a PhD student in the lab in France, Gilbert. So I've borrowed this slide from Stevens in a paper in 1980, just to remind those of you who don't know so much about speech, that speech is a typically broadband signals that contains energy going well, up to high frequencies, as you can see here on this spectrogram. And because this signal is broad, it's commonly believed that the cues that we use for decoding it, for recognizing the phonemes, are distributed across frequency. And an important notion in the development of intelligibility models is that of frequency importance functions. And this notion is that maybe the cues that we use for recognizing speech aren't distributed uniformly across the frequency axis, but some regions are more important than other regions, as illustrated here very schematically. And this notion is really at the heart of most macroscopic models of speech intelligibility, such as the articulation index, more recently developed into the speech intelligibility index, or the very recent speech recognition sensitivity model published in JASA by Musch and Bus. And so these models, the idea behind this model is that if you know the importance functions for a given speech material, and you know which part of the spectrums the listeners will have access to, then you can make predictions as to what the intelligibility is going to be. For instance, very schematically again here, if you know that you have a masker that falls mostly in regions that have low importance, then the prediction obviously will be that intelligibility will be little affected by the masker. Whereas if you have a masker that occupies mostly frequency regions that are important for recognizing speech, then the prediction would be that intelligibility will be substantially affected by the masker. So this leads to the question of how does one actually measure those frequency important functions that are so important for those macroscopic speech intelligibility models. And the traditional approach to measuring frequency importance functions has been to low-pass, using systematic high or low-pass filtering of the speech signals. So you start with a full signal as represented on the left there. Sorry, is there a laser pointer of some kind here? If not, it's... So here's the signal here, and I've represented the frequencies on the x-axis. Thank you, Eric. Thanks. And so that's the spectrum here. So you start with the full spectrum, and you measure intelligibility with this signal, and then you low-pass filter it somewhat, and then again you measure intelligibility, and you low-pass filter it again, like here, and then you measure intelligibility, and so forth. And by taking some kind of the derivative of this intelligibility function as a function of low-pass filter cutoff, you can get to the importance function. Now, this approach is working fairly well, but it has some limitations. One limitation comes from the fact that in real life, sounds are often not just filtered by some transmission channel, but also masker is added to it. So the main difference between filtering and masking is that in filtering, energy is removed, as we were doing before for measuring the importance functions, whereas with masking, you add energy here. And in some cases, the energy that is added, the energy of the masker that is added in some bands, can influence your ability to extract the information in other bands. Like in this case, for instance, if the masker is a low-frequency masker, there is a phenomenon in hearing which we know as the upward spread of masking, namely the fact that this energy here is going to mask some of the information that's present in that region here. And because of this effect, you cannot necessarily predict intelligibility in this situation based on measurements which you've taken with this kind of filtering approach. So one alternative approach to the filtering approach for measuring frequency important functions has been pioneered in recent years by Doherty and Turner et al., who published this work in JASA. And in this approach, you don't really filter the speech. You always present the broadband speech. But what you do is on each trial, each time you present the speech, you add noise in different bands. Like here, I've represented schematically 5 bands. And on each trial, you vary the signal-to-noise ratio in each band independently of the other bands and independently of the values before. And each time you measure as a function, you take, for instance, the first band, and you vary the SNR, and you collect recognition scores on each trial, and you do this over and over, over many trials, most of the time 1,000 to 2,000 trials. And in the end, a posteriori, you can plot the signal-to-noise ratio in the band of interest, say band 1 here, and as a function of or more exactly, the score that the listeners obtain as a function of this SNR. So here, I'm just plotting this for the binary score. Either subjects got it correct or they got it incorrect. And then you plot the score as a function of the SNR. And you can compute some sort of measure of association between those two variables. And in this case, you can use what's known technically as a point biserial correlation coefficient, which is just a correlation coefficient between one continuous variable and one dichotomous variable, namely the score here. And this correlation coefficient, which you obtain between those two variables, is going to tell you something about the importance of the considered band for recognizing the speech. Namely, if the correlation coefficient is relatively high, as in this example, you can think that this band is relatively important for understanding or for decoding the speech. However, like here, if you have a weak correlation between the SNR in a given band and the score, then you can think that this band is relatively unimportant for speech recognition. So some very preliminary results were obtained on a few subjects by Turner et al. In their 1998 paper with this method. The material which they used were the signals consisted of VCV stimuli, where the V was one of 3 vowels of the English language, A, I, U, and the consonant was one of 22 consonants of the English chosen randomly on each trial. And they used 4 bands, which the cutoff frequencies of which are indicated here, and they measured the correlation between the SNR in each of those bands and the recognition scores in 2 conditions. In one condition, all the bands were presented together, just like what I showed you in the previous schematic examples. And in another condition, they presented each band in isolation, just like you would do in the filtering approach, but this time varying the signal-to-noise ratio in that given band that you would present. And what they did is that they chose the band, the cutoff frequencies here were chosen such that when the bands were presented in isolation, they contributed about equally to the recognition of speech. Okay, so unsurprisingly, when you measure the importance of the different bands presented in isolation, as shown by the thick line here, you obtain about the same importance for all those 4 bands. However, when you do the same thing, you measure the correlation between SNR in each band and recognition score on the other hand, but you do it with all bands together, then you obtain dramatically different functions, which are shown here by the dashed lines. And you can see that, for instance, whereas this one was about equal contribution of each of the different bands, here, when you have all bands together, the curve is jagged. And for instance, this band is much more important than you would think when all bands are presented together based on if the band was presented alone. And one explanation which Turner et al. Proposed for explaining the fact that this band, for instance, was much less important than that one was that the energy contained in this one, and especially the first formant, was masking the information in that second band. Okay, so when you present bands together, you can get fairly different results as when you present them alone, and that justifies that goes at least some way toward justifying this method of presenting all bands together. One detail here that I'll explain now so that I don't have to explain it again when I present the results that we have obtained, because we're going to plot them on the same type of format, is that instead of plotting the row correlation coefficients which you obtain along this axis here, you normalize the correlation coefficients. You basically divide each correlation coefficient for each band by the sum of the correlation coefficients across bands. So you assume somehow that the sort of the total weight or total variance in your model is constant.
Let me ask you a question.
Sure.
So when you present the signal, all the bands together, you said that in every band you would have varying amounts of noise, and you plot this curve of a bivariate or two-value variable against whatever, the SNR.
Yep.
So the many samples that you have, let's say I'm doing this for band number 1. What are the conditions for band numbers 2, 3, 4?
They're independent. They're independent random variables.
Very independently.
Right.
So you expect an equal number with high and low SNR.
Yeah.
Here.
Yeah, the expected values are the same. So before I go on to describing the experiments that we did with this method, I just wanted to further justify our choice of using this method. And when we read those papers when those papers by Turner et al. Came out, we got pretty interested in it because they already start to point out in the paper, but also if you think about it a bit, you can realize the method can be used for different things. Of course, it's going to help better understand speech perception mechanisms in humans, by informing us about how listeners weigh information in different bands when the bands are presented together. But also, you can use the method if you can refine the importance functions which are measured. You can then come up, hopefully, with improved predictions from your macroscopic models of speech intelligibility. And one application that I was particularly interested in at the time was that you can hope and use this method to improve on the setting of multi-band auditory prosthesis, such as hearing aids or cochlear implants, because you can use this method to give you an indication of which bands are important for a given patient for recognizing the speech, and which bands aren't so important. And you can then use this knowledge to maybe tweak the parameters of the setting of the different in the different bands, or maybe to try and remediate, to try and train the patients to pay more attention to those bands that he or she is ignoring. So I'm now going to take you through the three main experiments or studies that we did with this method of the perturbation correlation to measure frequency importance functions. The first study was devoted to collecting sort of baseline or reference data in normal hearing listeners, which we could then use in future studies to compare what we obtain in normal hearing listeners to hearing impaired subjects, and also to provide baseline data for a reference condition, which we could then compare to frequency importance functions measured in other listening conditions, such as with interfering speech. So let's start with the first study, in which we sort of tried to get going with the method and collect data in normal hearing listeners. And in that study, we had 20 listeners altogether in two groups of 10 listeners each. And we had one group of younger listeners, aged between roughly 20 and 30 years, and one group of older listeners who were between 50 and 60 roughly. And the reasons we tested those two groups is that often when we test hearing impaired patients, there is a bias for those hearing impaired patients to be older than the younger people and than the younger controls. And therefore, we wanted to have sort of reference data in normal hearing listeners, both young and old, which we can later use as a reference basis, basically. And all those listeners had normal hearing for their age. The target signals which we used in that study were, like in Turner et al. Studies, VCVs with the vowel being A, I, or U, and the consonant was one of 17 French consonants, and most of these are consonants that you can also find in the English language. So this led to 51 combinations altogether, and each combination was uttered 4 times by each of 4 talkers, 2 male, 2 female, to produce a total of 816 target signals. And here are the technical details of the acquisition and playback. And most importantly, the signals were played back. The speech was at a level of 65 dBSPL peak as average over an 80 millisecond window. To these target speech signals, VCVs, we added noise, which we generated digitally such that it would have the same long-term average spectrum as the speech before we perturbed the level. And then we applied level perturbations in 5 different contiguous frequency bands, the cutoff frequencies of which are given here. And we chose those bands somewhat arbitrarily with the one constraint that their bandwidth should be sort of octave related. They would double as you go toward higher frequencies. So we could have done like Turner et al. And try and equate those bands for SII, but first, we didn't think that this would necessarily be the best thing to do, because they've shown that when the bands are presented together, the AI doesn't predict so well the importance of the different bands, because they start interacting. So it doesn't really make sense to use the AI necessarily to choose your bands. And the second reason is that for most practical applications, like if you use this in hearing impaired patients with multi-band hearing aids, the bands are going to be determined beforehand. You're not going to have the option to choose them. So the method should be flexible enough to accommodate arbitrary bands. And we varied the SNR in each band over a 24 dB range overall, plus 12 from minus 12 to plus 12, around a midpoint SNR, which we chose beforehand in each listener before doing the actual experiments, such that each listener would obtain around 68% correct. Here's the interface that we used to carry out the tests. It was all computer controlled.
So,
sure.
The level in each band was, the noise level in each band was the same across frequency?
The SNR, with the midpoint SNR, was the same, but it was adjusted overall to produce, on average, 68% correct in those listeners, in all listeners.
So relative level in different bands have got another relative level in speech.
Exactly, yes. It follows the speech spectrum. It's like speech-shaped noise. So we used a constant stimuli procedure whereby you present each time a signal with a random noise added to it, and then listeners respond as to what they heard, and they would indicate using this interface which consonant they'd heard and then which vowel they heard. And I forgot to say it was VCV, and the V initial and final V was always the same. And in order to count for a response to be counted as correct, it had to be correct both on the vowel and on the consonant. Okay, so here are the results that we obtained with this method, and I'm showing you first what we call the psychometric functions, which basically show the % correct score as a function of the SNR for each of the 5 different bands, from band 1 to band 5 here. And there are 3 observations that you can make on the basis of those psychometric functions to start with. First is that to a first approximation, a linear regression worked fairly well. Okay, so it's not like the data are severely, the relationship is severely nonlinear. So it seems that the use of correlation as a measure of association between SNR and % correct does, to a first approximation, a good job. The second thing that you can note on this graph is that already the slope of the regression line and the scatter around those regression lines differs somewhat across the different bands. So you can expect the frequency importance function not to be flat. And finally, you can see that here I've shown the results for the older group and for the younger group. And if you squint your eyes, you may be able to see that the difference in slope between the 2 groups differed itself across conditions. So you may expect different weighting functions in the older and younger listeners.
It sort of looks to me that as the signal-to-noise ratio gets better, there's sort of an asymptote some of these functions here?
Yes, yes. So we're currently working on a refined model where we're using second order and third order fits to those data, and I'm sort of working on the theoretical model behind it to sort of improve on the fits that we have. But the point here is that to a first approximation, we can use correlation.
So I don't understand why the ordinate data are not the same in all these plots. So you apparently weren't varying the band simultaneously.
We were varying the band simultaneously, but then you plot the percent correct base. It's conditioned on the SNR for that given band, so it's not necessarily the same. Actually, it should be different, I think. Does that answer your question, or?
No, I'll ask you later.
Okay. So now, if we take those correlations, correlation coefficients, or normalized correlation coefficients, which we extracted from the psychometric functions, and we plot them as a function of the band number, then the first question, of course, that we want to ask is, is what we are measuring reliable, or at least reproducible? Is it stable over time? So in order to test this, we had 2 sessions. The same week, listeners came 2 times, and each time they went through the 100 to 200 trials for each of the speech stimuli, and we measured the correlation, and then did it again on the next session. And I'm plotting the results of the two sessions, and you can see that to a fair extent, those functions largely overlap. So they're reasonably stable over time. Second question that you may ask when you are dealing with a sort of new or recent method is how do the results which you obtain with this method compare with results obtained with other methods, or at least in other studies? And so it's actually tricky to compare results which you've obtained with this method with given bands to results which have been obtained by other people using different bands, because you have to somehow convert everything into the same format, into the same bands. But with some simplifying assumptions, you can do this. And this is what we've done here. And I'm plotting now just the importance functions that I was showing you before for our study. And these are plotted with the field symbols. And I've superimposed onto those onto this plot, the results that were obtained by Turner et al. In the 1998 study using the same method. And you can see that, I mean, there are some differences, but in general, the functions, the shape of the functions is about the same. And in particular, they both peak on the 4th band here. And in fact, the fact that they both peak on this 4th frequency band is also in agreement with predictions that were made from the importance functions for nonsense syllables that were derived from the speech intelligibility index. So in that sense, there is some degree of agreement between the three approaches. The one method which led to markedly different results from those obtained with this correlational approach is the one by Katsuri et al. In 2002, who used a method that they call the spectral holes method, which is an extreme version of the correlation method. In that method, you put noise in different bands, but it's either on or off. There's no in between. Right? So it's like if on each trial you are trying to listen to speech through spectral holes. And this led to substantially different results. One thing which we noticed in the course of this study is that when we were plotting separately the importance functions measured in the younger listeners here and in the older listeners here as the empty symbols, there were some significant differences in shape between the two. And specifically, the older listeners were generally, high frequency bands were generally less important slightly for the older listeners than for the younger listeners. And concomitantly, because we're normalizing everything, the low frequency bands were slightly more important for the older listeners than for the younger listeners. So you might ask, what is the reason for this sort of lesser importance of high frequencies in the older group? And one obvious possible explanation is that I said both of the groups had normal hearing for their age, but when you actually look at the audiograms, the older listeners had elevated thresholds, absolute hearing thresholds on the high frequencies, especially 4 and 8 kilohertz, where the elevation was up to 20, almost 25 dB here. So it would appear from this that the audibility of high frequency information for those hearing impaired, for those older listeners was reduced. And when you once again, this is a tricky comparison, but I think it's better than nothing. If you plot the long-term average spectrum of the speech in third octave bands, which corresponds more or less to the auditory filter bandwidth here, and you superimpose onto this plot of the long-term average speech spectrum the hearing thresholds converted to SPL of the two listeners group, you can see that here is the audiogram of the older group, and in this group, hearing thresholds were in general as high, if not higher, than the level of the speech in third octave bands. So it's likely that the older listeners didn't have access to information in that fifth band, and that coincides or is in agreement with the fact that when you look at the correlation coefficients or weights obtained in this high frequency fifth band in those older listeners, it's not significantly different from 0. So here again, I've plotted the two. Another difference between the younger and older listeners was that I told you that we adjusted in each subject the midpoint SNR beforehand so that the subjects would all obtain about 68% correct. Well, in order to for the older listeners to have the same level of intelligibility as the younger listeners, we had to set the nominal SNR in the older people about 3 dB higher than in the younger people. Okay, so that's something that, by the way, is not accounted for by speech intelligibility index predictions. If you take our stimuli and with the noise and run it through the SII model, it doesn't account for this difference in speech reception threshold at 68%. And one other difference between the two groups, which sort of ties in with the difference in weighting functions between the two groups, is when you look at the percent of information transmitted for different phonetic features, such as voicing, nasality, frication, duration, or place. You see that whereas voicing and place weren't differently transmitted in the younger and older listeners, for affrication, this was less well transmitted in the older listeners than in the younger listeners. And it's known that the cue to fricative consonants are mostly in the high frequencies, and so if high frequencies are less important, then this is exactly what you would expect in the older listeners. So the conclusions of that first study is that, well, first of all, we wanted reference data in young and older listeners for later comparisons with other groups or in other conditions, and we got those data. The second is that the importance functions which we measured were fairly reproducible over time. They were stable, and they agreed pretty well with the data from other studies, especially using the same method. And we also almost incidentally found a difference between the young and older listeners, and we think that this difference, namely the fact that the high frequencies were less important relatively for the older listeners, ties in relatively well with the reduced audibility of high frequencies in this group and with the lesser transmission of fricatives in that same group.
Sorry, Don, could you go back to
Sure.
the previous plot? I don't understand this transmitted information, the y-axis. What are you measuring?
So you can think of it as simply the accuracy with which those different phonetic features were identified by the listeners.
Where the C was a fricative.
Yes.
And then you just, so this is the accuracy except you restrict yourself to those samples.
Yes, yes.
Okay.
It's like almost 1% correct, better than 1% correct on those features. Okay, in the second study, we now measured frequency importance functions in hearing impaired listeners. And these are just preliminary data because obviously this is something that's generally difficult to perform due to the duration of the test and the constraints. So we had 3 questions basically in this study. The first, is it feasible at all to measure frequency importance functions using this perturbation-correlation method in hearing impaired listeners? Because this had never been done before, and it still hasn't been done by anybody else than us, I believe. Second, do frequency importance functions in the hearing impaired listeners differ from those which we obtain in normal hearing listeners? And do they still differ even if you try and restore audibility? In other words, we're trying to ask the question, if you make things at the periphery as comparable as possible for the hearing impaired and normal hearing listeners, will they still differ in their in the way they assign importance to different frequency regions? So we're trying to peek into differences in listening strategies between two groups of listeners. And third, are the frequency importance functions different, the frequency importance functions which we measure in hearing impaired listeners, do they depend upon whether those listeners are used to wearing a hearing aid or not? And that question was inspired by previous work by Steve Gatehouse and others in Glasgow, who've showed the phenomenon which they've called acclimatation, namely a long-term change in perceptual abilities in hearing impaired listeners after they've worn for a long enough time a hearing aid. So in that study we had 12 hearing impaired listeners into 3 groups. One group was made of non-hearing aid wearers. Those were people who had never worn a hearing aid at the time we started the study. We had regular wearers who would wear a hearing aid binaurally for daily and for at least 6 months prior to the testing, often more than that. And those two groups were tested with spectral shaping, namely we tilted the spectrum of the speech signals before presenting it, such that the high frequencies were boosted. And that was done in an attempt to restore high frequency audibility. And in doing this, we used the Cambridge formula, or also called CAM filter, which was provided to us by those who developed it, Tom Baer and Brian Moore in Cambridge. And all those subjects were tested without their hearing aid. Okay, it was a barrier, and they were tested with under headphones. Okay, we took the hearing aids off, obviously. And finally, we had a group of control listeners who were or not hearing regular wearers, but those were tested without the spectral shaping, and that was just to test that when we don't have the spectral shaping, are the importance functions different? They should be. So here are just the audiograms of the 3 groups, and as you might have guessed, the non-wearers, the reason they weren't wearing a hearing aid at the time they were tested is that they had a bit less hearing loss than the others. So that's a factor in the potential confounding factor in our study. And the stimuli and procedure were basically identical to those which we used in the previous study that I showed you, except for the spectral shaping. So first of all, I should say that in order for all the subjects in those 3 groups, non-wearers, regular wearers, and controls, to have about the same percent correct on average, we had to set the midpoint signal-to-noise ratio substantially higher in the non-wearers than in the regular wearers and then in the controls. And of course, we had to set the SNR in those hearing impaired subjects higher than we did in the normal hearing subjects from the previous study. Okay, so here are the results which we obtained in the 2 groups of listeners, those that were tested with spectral shaping and those that were tested without spectral shaping. And this is to look into the effect of high-frequency amplification. And so if you compare the weighting functions which we obtained in the group tested with the spectral shaping, you see that there is more importance on the high frequencies than in the other group here. And so this sort of is in agreement with the idea that in this group, with spectral shaping, we boosted high frequencies, such that those high frequencies were more audible and therefore more usable by those patients. So this is sort of a sanity check on the method. We just wanted to make sure that the high frequency boosting would have the expected effect. Now it's kind of interesting because if you look at these functions with the spectral shaping, they look, at least at first sight, in shape, similar in shape to those which we obtain in normal hearing listeners, in the sense that we had the highest importance on the 4th frequency band. So it seems that to some extent, boosting high frequencies is going to restore importance functions in those hearing impaired subjects. The second the second outcome of this study in hearing impaired listeners was when you compare the weighting functions which were obtained in hearing impaired listeners who would never used a hearing aid prior to testing with those obtained in listeners who had used a hearing aid for at least 6 months prior to testing, you can see that in general the importance functions in the hearing impaired listeners who had used the hearing aid regularly were more like those of the normal hearing listeners, which I've shown here as the thick line. So the conclusions of that study in hearing impaired listeners are that, first of all, frequency importance function can be measured in hearing impaired listeners using the exact same method as I described you before, with little change in stimulus parameters. The preliminary results which we obtained in those listeners are consistent with, of course, they do not demonstrate that first, frequency importance functions are sensitive to high frequency amplification. We got a change in frequency importance functions between the group that had high frequency amplification and the group that didn't. And second, they are consistent with, they don't yet provide a clear demonstration of that, but they are consistent with the possibility that regular wearing of a hearing aid, which provides high frequency amplification, may have a long-term influence on the listening strategies. But this is more like sort of hand-waving and interesting possibilities for future studies. It is obvious that we need a lot more patience in order to make a stronger claim on this here. And finally, I'd like to talk about the study which, at least to me, is perhaps the most interesting of the different studies which we perform with this method, which concerns what happens when you add interfering speech to the speech which the subjects are trying to recognize. How do the importance functions change in that context? So that was the question which we had. The general question was, how do frequency importance functions for speech recognition, as measured using this perturbation-correlation approach, depend on the listening conditions? Is it the case that certain bands become more or less important in certain types of environments, such as when you have noise versus competing speech, as we will compare here? And this is a first step toward trying to figure out what the listening strategies of like in that case, normal hearing listeners are in different situations, different contexts. Maybe that the importance that we give to different parts of the spectrum are not at all the same, depending on the kind of interference that we're trying to cope with. So in this study, we had 15 normal hearing listeners. They were generally young, between 20 and 30. The target signals and the noise were exactly the same as in the previous study, with this time no high frequency amplification, obviously. And we added to the target signals and the noise which the subjects had to recognize a babble background, which was produced by, we took the VCV signals, which we had initially recorded, and then we cut pieces of them, windowed them, and then mixed them and pasted them all together to produce a sort of multi-talker babble. So I was sort of a bit wary of playing demonstrations here because I'm going through the speakers of the PC, so that may not sound very nice, but let's give it a try. First, this is the just examples of the babble alone, babble background. So this is very noisy, it's saturating, obviously, but you can get the idea. And here are the, now when you have the target signal alone, IGI, and then when you present the same target signal added to the babble background. Right, and listeners had to report only VCV in there, entire whole VCV in the stimulus. And so the nice thing about generating the babble signals from the speech which we used as the target is that when you look at the long-term average spectra of the two, they were similar, except that this is the long-term average spectrum of the speech signals which we used, and here is the long-term average spectrum of the babble signals, the background. But we set the difference, the sort of vertical translation between the two is due to the fact that we set the babble 5 dB below the level of the speech. Obviously, we didn't want complete masking. And then we took this mixture of babble plus target and added the noise and chose once again the midpoint SNR in such a way that on average listeners got 66% correct roughly in the no babble condition, and about the same thing, it wasn't statistically significantly different in the babble condition. And in order for listeners to perform as well in the babble condition as in the no babble condition, we of course had to raise the nominal SNR in the presence of the babble, as you would expect, by about 8 dB. One thing which I should have shown you before is that when you start looking at the error rates per, not just overall, but per consonant and per vowel, most of the errors were made on the consonants. The vowels were almost always accurately identified. So those weighting functions, they tell you mostly something about consonant perception in that case. And here, before looking at the frequency importance functions themselves, I'm plotting the, once again, transmitted information for the different features. And you can see here that this is the condition without the babble, and here is with the babble. In general, the percent transmitted information was less, as you would expect, in the presence of the babble than in the absence of it. And the most dramatic reduction was for the affrication and duration features. Okay, now if we look at the psychometric functions which were obtained in each of those 5 different bands, first without the babble, that's the reference condition, and then with the babble added, we see once again that the functions are to a first approximation, and once again this is to be taken with a pinch of salt. We're actually working on sort of improving the fits using higher order modeling. But to a first approximation, we can go on with what Turner et al. And others have used and use just correlation between the 2 variables here. And the second thing is that the slope of the regression lines was usually steeper without the babble than with the babble. And this is sort of what you would expect, because the babble is an additional source of variance in the bubble, which you're not in fact taking into account here, because your only predictor is the SNR based on the background noise, not on the babble. But importantly, the difference in slope between this condition and that condition was not always the same across the different bands. And we're going to get into this, but already this gives you a hint that the weighting functions, the importance functions, are not going to be the same in the 2 conditions. And this is what is shown here, where I've plotted once again the relative weight of the different bands for each of those 5 frequency bands. And here are the results obtained without the interfering speech, without the interfering babble. And here are the results in the same listeners with the interfering speech. And you can see 2 things. What happened is that when we introduced the babble, the importance of high frequencies went down, and concomitantly, of course, the importance of low frequencies, the bands, the first 2 bands, went up. So frequencies below 750 Hertz, when you add the babble, they become relatively more important. So why did the low frequencies become more important when you are trying to understand speech and interfering speech? Why do you rely more on low frequencies? Well, we haven't figured that out for sure yet. There are a number of explanations that need to be considered. But we've started already to look into possible explanations. And one of them is that the babble signals, I've shown you here a few examples of those sonograms of those babble signals. And they were, as you can see, heavily amplitude modulated. So it's not like we had taken so many Stokers put together that it was approximating white noise. It was still containing a fair amount of envelope fluctuation. And it's been shown by several authors in recent years that at least normal hearing listeners can take advantage of such fluctuations in the masker by selectively listening in the valleys of the masker, the temporal dips, in order to pick at the signal. Okay, so because often it's likely that when you have a dip in the masker, you may have at the same time have a peak in the signal which you're trying to hear. So this has been called dip listening or temporal dip listening. You're listening in the deep selectively, basically, to try and hear out the target. And this explains that you get better results in normal hearing listeners when you're using this kind of modulated background as a masker as when you're using flat noise. And so we thought maybe there is more opportunity for dip listening at low frequencies, and this is why we're relying more on low frequencies when we're trying to cope with a modulated masker. in order to test this idea or go some way toward testing it, we took all the babble signals which we used in our study, run them through a gamma chirp auditory filter bank, and then extracted the envelope using half-wave rectification and low-pass filtering below 50 Hertz. And I'm showing you here two indices extracted on the envelope, which are usually employed to quantify the depth or the amount of amplitude fluctuations in those, at those different frequencies, and they're basically telling the same story. That was just a check. But what they show is that, on average, envelope fluctuations were not systematically larger on the low frequencies, as you can see here, as they were in other frequency regions. So it doesn't seem likely that the reason for which we're relying most on low frequencies when coping with interfering speech is that we have more opportunity for listening selectively in time at the output of those filters that are tuned to low frequencies. Another potential explanation, which I think is more likely, is relates to frequency selectivity rather than temporal mechanisms. And it's the idea is that in order to identify target vis-a-vis signals in the presence of interfering speech, you first have to pull apart the target signals from the interfering babble before you can recognize them. So that will entail or involve some auditory segregation mechanisms. And a common cue, acoustic cue, which is used for segregating simultaneous talkers, is F0 differences, because it's often the case that when two people speak, they don't have exactly the same voice pitch or F0. And you can take advantage of this, or your auditory system can take advantage of this in order to segregate one talker from the other. But we've shown in some experiments, well, Bob Carlyle in 1996 and more recently with Andrew Oxenham, we've shown that in order to take advantage of F0 differences for segregating concurrent sounds, you need to have a fairly good frequency resolution. And we know that frequency resolution is better at low frequencies. So that might explain why, when we're trying to disentangle speech from interfering speech, we're looking mostly at low frequencies. So this idea, it's not yet a conclusion, is consistent with the idea that fine spectral resolution may not be necessary for understanding speech in quiet. That's been shown by, in a science paper by Shannon et al. But it may be very important for understanding speech in complex spectral backgrounds, such as interfering babble. So the conclusions of that study are that frequency importance functions measured in the absence and in the presence of interfering speech are different. In the presence of interfering speech, low frequencies become relatively more important and high frequencies concomitantly less important. And this does not seem to, due to there being more opportunity for temporal dip listening at the output of low frequency auditory filters, but it could be due to the auditory filter bandwidth being smaller at lower frequencies and this facilitating segregation of the signals which you're trying to hear out. And so the general idea that comes out of this third study is that frequency importance functions can differ depending on the listening situation, and therefore, as such, they may provide a tool that can be used in future studies for getting some insight into the listening strategies that are used in different listening environments. So by no means this completes the series of things that could be done with this method. We think it's a pretty interesting and promising method. But there are some open questions with it, and we're currently trying to look into this with my colleague Gaëtan and people at MIT. And one concern with the method is that it's pretty time-consuming. So if we want to really import it into the clinic, we'll have to find a way of speeding it up. Generally, the way we speed things up in psychophysics is by using adaptive procedures that will sort of immediately tune into the range that is of interest for measuring whatever we're trying to measure. But the problem with that is that there is one basic assumption of the method for computing the correlation, which is that the SNR in the different bands vary independently. Now, if you start to try and use an adaptive method that will tune the SNR to the right range, this is likely to introduce correlations in SNR across bands. So we're trying to overcome this difficulty. And there are some theoretical questions, like, for instance, in this application, in the way this method is applied to a complex signal such as speech, you cannot, at the moment, disentangle or distinguish between external, that is stimulus-related, and internal, listener-related factors of the importance. In other words, when you find that a band is important, you don't really know whether it's important because intrinsically it contains more cues than other bands, or because listeners are paying especially attention to that particular band, or both. And in which case, if it's a bit of both, then we'd like to know what's the relative contribution of each of these two factors. So a question for future studies, I think an important one is, can we somehow disentangle the contribution of stimulus-related properties and in the different bands, and the contribution of internal weights or attention, whatever you want to call the listener-related factors. And so I just wanted to acknowledge the fact that this work was supported by CNRS in France, and thanks to those people for coming up with a lot of interesting comments as we were writing the papers or working on the study. And I thank you very much for your attention.
So a simple hypothesis would be that F1 spends more time in your low frequency band than F2 spends more time in the high frequency band. So if you just plot the distribution of F1 and F2 in your data, in your samples, is it a qualitative explanation?
Yeah, so we looked at for those signals which we used, we extracted we measured the form and frequencies and quantified all this. But are you referring specifically to the Babel study?
No, let's say for just the shape of the importance function. Going
right.
back to the early experiments, shape of the importance function in normal listeners was kind of peaked at. It would look like too high a frequency band. Would that be the explanation for me? But I don't know what you're.
Yeah, well, so you're saying because F1 is more likely to live in the low frequency bands, then those bands should be more important. Is that what you're saying?
Well, the F1 and F2 tend to be in certain frequency bands, and they might be less likely in 750 to 1750. And so in one case, listeners are more focused on F2. In another case, they're shifting their attention to F1, or that, whereas I'm just free associating here.
Yeah, no, it's interesting.
I was sort of asking what the data looked like in terms of where the performance source is.
Well, this we can sort of, when you look at the SII, I showed you on the earlier slide that the frequency importance functions which we measured weren't that different from the ones measured with the SII, at least for the nonsense syllables in our case. And so, and the peak in the importance functions, I think you noticed, is on the fourth band. So it seems that there's it's not so much the lower bands where you would expect the first formant to fall that are the most important. The most important one is this one here, where I think, so I'm not a psycholinguist, but when I talk to people in Ken Stevens' lab, or they tell me that information for fricatives is expected to fall in that kind of high frequency region. And the other part of your comment, which I find interesting, is that you're saying, or you're hinting at the possibility that maybe listeners can adjust their weight on the fly, basically online, depending on where the formant positions are. So this is beyond the scope of what we can address with this kind of method, because here we're in the domain of macroscopic models, which rely only on the long-term average spectrum of speech. And of course, it would be interesting to try and do this, to apply the same kind of method, but on a short-term way, in order to try and figure out how the weights vary depending on where the information falls. And people are slowly starting to do this. There's a recent paper in JASA by Bacon and Apu, in which they've tried to apply this method, but instead of varying the signal-to-noise ratio, they varied the amount of, the masker was amplitude modulated in each band, and they varied the amount of amplitude modulation in each band relative to the speech. So they're getting at sort of a combined spectral, temporal weight importance functions.
In the last case, when you're talking about the Babel noise, if your hypothesis is that people are essentially trying to separate sources,
yes,
and that's what decides the shape of the importance function, then perhaps one way to do this might be to change the task but use the same kind of noise. Let's say make the task recognizing a speaker. Is it or is it not the same speaker as the, let's say you present a clean stimulus and
right.
present a noisy one, and they have to decide whether or not it's the same speaker.
Yes.
Then the importance they give to various bands in that task should be very much like recognizing the syllables themselves, because if the hypothesis is that all they're trying to do is, or a big component of what they're trying to do is track that source.
Yes, so maybe it's not as simple as I wasn't trying to say that it's the weighting functions in the case of the interfering babble are determined only by segregation mechanisms. It's a mixture of basically recognition mechanisms and segregation mechanisms. So if you do the kind of task that you suggest and ask to identify a listener instead of now trying to recognize speech, you're dealing with a whole different task altogether. And I'm not sure we would be still getting at the same question, but it would still be an interesting thing to try.
The other thing I was thinking of is that if there were certain, you had another picture where you had the individual features, either voicing or frication or something.
Mm-hmm.
And there, if you could identify a feature which was easy to track in time in the presence of noise, then there might be a correlation between the errors of, let's say for argument's sake that nasality is easy to track even if there is noise.
Mm-hmm.
Then perhaps the other errors, so now this is only one feature and you're looking at its errors. If you look at pairs of features, maybe there will be a relationship between when you make an error in the nasality detection, you're also likely to make an error in the duration or the friction or whatever else. Because essentially you're failing to track the source. And so since this is most closely related to tracking the source, the others kind of follow it.
That's an interesting point. You're saying basically the different acoustic features, they may be distributed differently in time, over time. Some may be over the long run and others may be more localized.
So there might be a correlation between being able to detect one kind of feature and another.
Yes.
And the reason might well be that what's really going on is that they're trying to track that one signal in noise, and one feature is most indicative of their success in tracking. And when they succeed in that, all the other recognition follows, and when they fail in that, everything else follows.
That's a good point. Yeah, well, I think this is something we can look into based on the data that we have already. So we'll go back to this and try and address it.
So I think this is a related comment or related question. We're in the third series of experiments when you were talking about mechanisms that may be based on dip listening versus filter bandwidths. Would that predict, with those two mechanisms, differentially influence the ability to identify the consonant versus the vowel? If you looked at consonant versus vowel errors, would that tell you a little bit more about what the strategy might be?
Yes, so I mean, I showed you the error rates for vowels and consonants, I think, and it's you can see that if you consider vowels errors on the vowel only, not accompanied by an error on the consonant, and this was like less than 2% of the errors altogether. So, to me, this suggests that the information we're getting with these importance functions, what they measure is mostly consonant perception. More than vowel perception. Does that answer your question?
Well, I was wondering about it in the context of the third set of experiments with the babble in the background. If
I see.
The time window of the dip, for example, might affect a consonant in a different manner than the vowel.
I see.
Or
Yeah.
the filter might affect one differently than the other.
Yes, I must say that I was a bit wary of going into this kind of detail analysis because I'm a psychophysicist and not so much a speech scientist. So I'm not very much used to how the different acoustic or the phonemic features relate to acoustic cues and how you could use this. And if on top of that you're trying to look at different parts of the spectrum, then this is definitely something that's interesting. But it seems like a daunting task. But I'm hoping that someone will help us in doing this kind of thing. It's an interesting suggestion.
So I would think one of the advantages of this experimental technique would be that you could look at interactive effects between bands on accuracy. So is there anything to be in mind along this?
Yes, that's the hope. So I mean, I think there are two parts in order to get to a model of intelligibility that will adequately address the problem of interaction between bands, which current macroscopic models such as the SII do not do. We'll have to first make sure that the importance functions which we measure already sort of reflect or take into account those interactions between bands. But also then when we feed those importance functions into macroscopic models, then we'll have to again take into account the fact that the information is not independent, based both on the master and on the signal. So yeah, but that's the hope. It's the idea is to try and because, for instance, there are experiments by Warren and others who have shown that if you ask people to recognize speech filtered through a narrow spectral slit of, say, 1/3 of an octave in low frequencies, and then you measure intelligibility with that, and you do it again, but this time filtering through a 1/3 octave band at high frequencies, and you measure intelligibility, then the scores that you will get for each of those two bands presented in isolation are much worse than what you do if you present the two bands together because of synergetic interactions between the two.
Hearing impaired listeners typically have particular difficulty in computing backgrounds. Do you think you would see anything different or learn anything interesting by doing the Babel, looking at the Babel analysis with hearing
Yes,
impaired?
yeah, that was the hope actually when we started, when Gaëtan started his PhD, I set up a program that was for 10 years of work, and we were hoping we would get by those studies in 6 months, and then the hope was to apply test the difference in listening strategies also in hearing impaired listeners. And the hope, the end goal was to, if we find, for instance, the growl, most of this kind of research would be, if you find differences between hearing impaired listeners who are successful with their hearing aid and listeners who aren't, and you see a difference in weighting functions, then maybe you can train those listeners that do not assign the importance to the right regions by maybe forcing the SNR in those regions to be especially high when you force the SNR in the other bands, which they shouldn't pay attention to low values, and train them with that, and hopefully see that you can improve performance in the long run, those kind of things. But it's pretty challenging already to use this method as it is now, as it stands, because it's really time consuming. It's like 2 hours per subject to measure the one set of psychometry of importance functions. So doing this in hearing impaired listeners was already pretty hard. If we on top of that we had the Babel, then I'm not sure we're going to be able to do it, but it's something that ought to be done.
Is the reason it's so long is because you have these 5 bands, and each band you have...
Yes, that's...
You're sort of trying to cover this whole space.
Yeah, that's combinatorial explosion, basically.
So perhaps what may be useful instead of doing this uniform sampling on all the 5 bands, once you have an idea where the function has the highest slope,
yes,
you may be able to do the sample SNRs differently, and you sample more in
yeah,
the region where you think there is going to be a change and less where you think it's going to be flat.
Yes, I'm currently thinking about this, and I'm trying to work out the math behind basically the method. And I think that, in fact, although we went for what Turner et al. Had already done, namely using a uniform sampling range for the SNR, it would be much wiser, even mathematically, for the method to provide optimal results, to use Gaussian distributions for the SNRs in the different bands. So we're going to try that.
But of course, when you do the linear correlation, you don't see it because on your x-axis you have equally spaced SNRs. But if you see the nonlinear effect,
yeah,
you'll be able to decide better.
Yeah, that might go some way toward optimizing the method, but you still need the independence between the SNRs in the different bands, and so there's not much you can do against combinatorial explosion with that, basically. I think there are no more questions. Well, thank you very much again.